Tonight, we're going to talk about something buried in the geological record that scientists can't fully explain. 56 million years ago, something released thousands of gigatons of carbon into Earth's atmosphere in just a few thousand years. That's more carbon than all of human industry combined. The isotope signature looks exactly like burning organic material, exactly like what we're doing right now, and nobody knows what caused it. By the end of tonight, you're going to understand why this mystery has scientists questioning everything we thought we knew about Earth's deep past and what it could mean for our own future. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In 2018, two scientists published a paper that most people ignored. Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and Adam Frank, an astrophysicist at the University of Rochester, wrote a paper with a question that sounds like science fiction. Could industrial civilization exist in Earth's geological record, and we just wouldn't know? They called it the Silurian hypothesis, named after an episode of Doctor Who where reptilian beings evolved before humans. But this wasn't science fiction. This was serious research published in the International Journal of Astrobiology, and what they discovered was deeply unsettling. They started with a simple thought experiment. Imagine humanity disappeared tomorrow. Every city, every road, every piece of technology we've ever built, gone. Fast forward 10 million years. What would remain? What traces of our civilization would a future geologist find in the rock record? The answer shocked them. Almost nothing. Buildings crumble. Cities erode. Even our most permanent structures, the pyramids, Mount Rushmore, the Great Wall of China, all of it breaks down relatively quickly on geological timescales. Concrete lasts maybe a few thousand years. Steel rusts. Glass shatters and gets ground into sand. Within 10,000 years, most physical evidence of our cities would be gone. Within 100,000 years, the landscape would look almost natural again. Forests would reclaim the land. Rivers would erase the scars we left, and erosion would smooth everything over. But Schmidt and Frank weren't talking about 10,000 or 100,000 years. They were talking about millions of years. On that timescale, the Earth's surface is constantly being recycled. Plate tectonics drag ocean floors down into the mantle where everything melts. Mountains rise and erode away completely. Sediments get buried miles deep, heated, compressed, transformed into new rock. The oldest ocean floor on Earth is only about 200 million years old. Everything older than that has been subducted, pulled down into the Earth's interior and destroyed. The continents are older, but their surfaces are constantly being reworked by erosion, weathering, and geological processes. Very little survives intact from more than a few 100 million years ago. So here's the disturbing question. If we disappeared tomorrow and came back 50 million years later as geologists trying to find evidence of our own civilization, what would we actually be able to detect? Schmidt and Frank ran the numbers. They built models. They looked at what traces an industrial civilization would actually leave in the geological record, and they found that there are only a few things that would survive. Chemical signatures in rock layers, changes to isotope ratios in sediments, spikes in certain elements or compounds that don't appear naturally, plastic particles, synthetic molecules that don't exist in nature, radioactive isotopes from nuclear testing, and most importantly, a massive spike in carbon dioxide concentrations preserved in ice cores, ocean sediments, and the chemistry of ancient rocks. That's it. That's all that would remain of us. No buildings, no artifacts, no clear fossils of our technology. Just chemical fingerprints in the rock. And then they asked the really terrifying question. Are there any unexplained chemical fingerprints in Earth's geological past that match what an industrial civilization would produce? The answer was yes. 56 million years ago, something released an enormous amount of carbon into the atmosphere in a geological instant. It's called the Paleocene-Eocene thermal maximum, usually shortened to PETM, and it's one of the biggest mysteries in geology. The PETM is not a secret. Geologists have known about it for decades. It's studied extensively. Textbooks describe it as a natural climate event, a sudden warming period triggered by volcanic activity or methane release from the ocean floor. But here's what those textbooks often don't emphasize. The amount of carbon released during the PETM is staggering. Estimates suggest somewhere between 3,000 and 7,000 gigatons of carbon were released into the atmosphere over a period of several thousand years. To put that in perspective, humans have released about 400 gigatons of carbon since the Industrial Revolution began. The PETM released roughly 10 to 15 times more than all of human industry combined. And it happened fast. Geologically speaking, it happened almost instantly. The entire event played out over maybe 20,000 years, possibly as little as 5,000 years. In geological terms, where events are usually measured in millions of years, this is a blink. One moment the climate was stable, the next moment it wasn't. Global temperatures shot up by 5 to 8 degrees Celsius, or 9 to 14 degrees Fahrenheit, in just a few thousand years. The oceans acidified dramatically as carbon dioxide dissolved into seawater. Species went extinct. Ecosystems collapsed and reformed. Deep-sea organisms died off in massive numbers. Terrestrial animals migrated toward the poles, trying to escape the heat. It was a planetary crisis. And when it was over, Earth was a different place. But here's where things get strange. The chemical signature of that carbon doesn't match what you'd expect from a purely natural event. When geologists analyze rock samples from the PETM, they look at something called carbon isotope ratios. Carbon comes in different isotopes, mainly carbon-12 and carbon-13. Plants preferentially absorb carbon-12 during photosynthesis because it's slightly lighter. So, organic carbon, carbon that came from living things, has a different ratio of carbon-12 to carbon-13 than inorganic carbon from rocks or volcanic emissions. When you burn fossil fuels, you're burning ancient organic matter, plants, and organisms that died millions of years ago. That organic carbon has the same isotopic signature as living plants. It's depleted in carbon-13. During the PETM, the carbon isotope ratios in rock layers show a massive spike in carbon-12. The ratio shifts dramatically toward the light isotope. This is called a carbon isotope excursion, and it's exactly what you'd see if someone burned enormous amounts of organic material or fossil fuels. It's the same signature we're creating right now with our industrial emissions. The rocks from 56 million years ago look chemically identical to what we're doing today. This has been known for decades, but it's usually explained away. Geologists say it must have been methane. Methane is organic in origin, made by bacteria breaking down organic matter in oxygen-poor environments like deep ocean sediments or Arctic permafrost. Methane has the same carbon-12 enrichment as plant material. If something triggered a massive release of methane from the ocean floor, it could produce the carbon isotope signature we see in PETM rocks. The problem is, no one can fully explain where that much methane would come from, or what would trigger such a massive sudden release. The leading theory involves something called methane clathrates. These are ice-like structures that form in deep ocean sediments under high pressure and low temperature. Water molecules cage methane molecules in a crystalline lattice. Billions of tons of methane are stored this way in ocean sediments around the world. If something warmed the ocean enough, these clathrates could destabilize and release their methane all at once. Methane is a powerful greenhouse gas, 25 times more potent than carbon dioxide over a century. If enough methane was released, it would warm the planet rapidly, which would destabilize more clathrates, releasing more methane, creating a runaway warming feedback loop. This is the conventional explanation for the PETM. Volcanic activity warmed the oceans slightly, triggering an initial release of methane, which warmed things further, triggering more methane release, and so on. It's plausible. It fits the data reasonably well. But there are problems with this explanation. First, the amount of methane required is enormous. You'd need to destabilize a significant fraction of all the methane clathrates in the world's oceans simultaneously. That's a lot of methane, stored in many different locations at different depths, with different stability conditions. Getting it all to release at once requires a very specific and powerful trigger that would have to affect the entire global ocean. Second, the timing is too precise. Methane clathrate destabilization should be gradual. As temperature rises, clathrates in shallower water destabilize first, then deeper ones. It should ramp up over tens of thousands of years at least, not happen in a sharp spike over just a few thousand. Third, and this is where things get interesting, the carbon isotope signature doesn't quite match pure methane release. Methane from clathrates is extremely depleted in carbon-13. But the PETM carbon signature, while shifted toward carbon-12, isn't as extreme as you'd expect from pure methane. It looks more like a mix, like something burned both organic material and released some methane, or like something burned fossil fuels. Coal, oil, and natural gas have isotope signatures that fall right in the range we see during the PETM. They're organic in origin, so they're enriched in carbon-12, but not as extremely as pure methane. If you wanted to create the exact carbon signature we see in PETM rocks, burning massive amounts of fossil fuels would do it perfectly. Of course, 56 million years ago, there were no humans to burn fossil fuels. So the conventional explanation stands. It must have been methane from natural sources, combined perhaps with some organic carbon from destabilized ocean sediments or burning peat deposits. But no one has definitively proven this. The mechanism remains unclear. The exact source of the carbon is still debated, and the sheer volume of carbon released in such a short time continues to puzzle geologists. This is the gap Schmidt and Frank identified. An unexplained carbon event that matches exactly what an industrial civilization would produce. Let's be clear about what the Silurian hypothesis actually proposes. Schmidt and Frank are not claiming there was an ancient industrial civilization. They're not saying aliens or lost Atlantis or any of that. What they're saying is more subtle and more scientifically important. They're saying that if such a civilization existed, we might not be able to detect it, that our methods for studying deep time have a blind spot. that the geological record could hide things we assume it would reveal. This is important because it changes how we think about looking for life elsewhere in the universe. If we can't even detect our own civilization in the geological record after 50 million years, how would we detect alien civilizations on other planets? If we drill core samples on Mars or analyze rocks from exoplanets, what would we actually be able to see? This has direct implications for the search for extraterrestrial intelligence and for understanding the Fermi paradox. The Fermi paradox asks why, if the universe is so vast and old, we haven't detected any signs of alien civilizations. One answer is the Great Filter, the idea that something prevents civilizations from surviving long enough to spread across the galaxy. Maybe that filter is ahead of us. Maybe civilizations inevitably destroy themselves through war, environmental collapse, or resource depletion. Maybe intelligence itself is self-limiting. Maybe every species that develops technology eventually uses that technology to make its own planet uninhabitable. The PETM could be evidence of exactly this pattern. A rapid industrialization, massive carbon release, runaway climate change, and then silence. Whatever caused the PETM ended relatively quickly on geological timescales. The carbon spike is sharp in the record. It rises fast and falls fast. Within about 200,000 years, carbon levels returned to normal. The climate cooled back down. Life recovered. If the PETM was caused by an industrial civilization, that civilization didn't survive its own environmental crisis. It burned through its resources in a geological instant and then vanished, leaving only a chemical fingerprint in the rock. Now, before this sounds too much like ancient aliens or conspiracy theory nonsense, let's pump the brakes and look at what actually makes sense here. The Silurian hypothesis is not saying this happened. It's saying it could have happened and we wouldn't necessarily know. That's a very different claim. It's about the limits of our detection methods, not about actual evidence of ancient civilizations. That said, the evidence from the PETM is genuinely strange. And it's worth looking at seriously, because even if there was no ancient civilization, understanding the PETM tells us something critical about our own future. The PETM is the closest geological analog we have to what we're doing right now. We're releasing carbon at unprecedented rates. We're warming the planet rapidly. We're acidifying the oceans. We're driving species extinct. Everything we're doing matches the pattern from 56 million years ago. The PETM gives us a preview of what happens next. During the PETM, sea surface temperatures in the Arctic reached about 23 degrees Celsius or 73 degrees Fahrenheit. That's warmer than Miami's average ocean temperature today. The Arctic Ocean was subtropical. Palm trees grew in Wyoming. Crocodiles lived in the Arctic Circle. Deep ocean temperatures rose by 4 to 5 degrees Celsius, or 7 to 9 degrees Fahrenheit. Which doesn't sound like much until you realize how much energy it takes to heat the entire deep ocean by even 1 degree. The amount of heat absorbed by the oceans during the PETM was staggering. Ocean chemistry changed dramatically. The pH dropped as carbon dioxide dissolved into seawater, forming carbonic acid. This acidification dissolved the shells of many marine organisms. Entire groups of deep-sea foraminifera, tiny shell-building plankton, went extinct. Their shells literally dissolved in the acidified water before they could be buried and preserved as fossils. The loss of these organisms disrupted ocean ecosystems for hundreds of thousands of years. On land, mammals underwent dramatic changes. Many groups of mammals that existed before the PETM went extinct or were replaced by new species better adapted to the warmer climate. Early horses, which were small forest-dwelling browsers before the PETM, evolved rapidly during and after the event into larger forms adapted for more open environments. Primates, our distant ancestors, underwent significant diversification during this time. The PETM created new ecological opportunities that drove evolutionary innovation. But the cost was mass extinction of species that couldn't adapt fast enough. The recovery took hundreds of thousands of years. Carbon levels slowly declined as natural processes removed it from the atmosphere. Chemical weathering of rocks consumes carbon dioxide over long timescales. The oceans gradually absorbed carbon and buried it in sediments. Plant growth on land pulled carbon out of the air and stored it in soil and biomass. But this recovery was slow. It took roughly 200,000 years for the climate to stabilize at a new normal. During that time, ecosystems were in constant flux, species were going extinct and evolving, and the planet was fundamentally different from what it had been before. The PETM reshaped Earth. And we're recreating the same conditions right now. Our carbon emissions are rising at a rate that matches or exceeds the PETM. Our climate is warming faster than at almost any point in geological history. Our oceans are acidifying at rates not seen in 56 million years. If the PETM was caused by natural processes, and those natural processes nearly broke the planet's ecosystems, what does that say about what we're doing intentionally? If it was caused by something else, something we don't fully understand, what does that say about our ability to predict and control what happens next? This is why scientists are terrified. Not because they think there was an ancient civilization, but because the PETM proves that Earth's climate can change catastrophically fast, and when it does, the consequences are severe and long-lasting. We're running the same experiment again. We know how it ended last time. Let's talk about what would actually survive from our civilization if we disappeared today. Schmidt and Frank worked through this systematically. What physical artifacts would persist in the geological record? Plastics are obvious. We've created an entirely new category of materials that don't exist in nature. Synthetic polymers, compounds made from petroleum that won't biodegrade on any reasonable timescale. Plastic bottles, bags, microplastics in the ocean. All of it is accumulating in sediments right now. If you drilled a core sample from ocean sediments millions of years from now, you'd find a distinct layer enriched in plastic particles. It would be a marker horizon, a thin layer that marks our existence as clearly as the iridium layer marks the asteroid impact that ended the dinosaurs. But plastic degrades eventually. UV radiation from sunlight breaks it down into smaller and smaller pieces. Microplastics become nanoplastics. Eventually, over millions of years, even plastic probably breaks down into simpler organic molecules. It might leave a faint chemical signature, an unusual concentration of certain hydrocarbons, but it wouldn't be obvious. Synthetic chemicals are another marker. We've created thousands of compounds that don't exist naturally. Pesticides, pharmaceuticals, industrial chemicals, PCBs, flame retardants, all of it is being released into the environment. Some of these compounds are extremely stable. They persist in soils and sediments for decades or centuries. A few might persist for millions of years, leaving faint chemical traces that a sophisticated analysis could detect. But again, these traces would be subtle. You'd have to know what to look for, and you'd need extremely sensitive detection methods. A geologist in 50 million years looking at a rock sample probably wouldn't notice anything unusual unless they were specifically testing for synthetic organics. Radioactive isotopes are more definitive. Nuclear weapons testing in the 1940s and 50s released radioactive isotopes that don't occur naturally, at least not in the concentrations we created. Plutonium-239, carbon-14 from atmospheric tests, cesium-137, strontium-90. These isotopes will persist for thousands to millions of years. They're being incorporated into sediments right now. A future geologist could detect them and know that something unusual happened. But here's the catch. Radioactive isotopes decay. Plutonium-239 has a half-life of about 24,000 years. After 10 half-lives, which is 240,000 years, the concentration drops to less than 1,000th of its original level. After a million years, it's essentially undetectable. Carbon-14 has a half-life of only 5,700 years. It's gone even faster. So, nuclear fallout leaves a signature, but only for a geologically brief period. After a few million years, it fades into background radiation. Metal deposits could theoretically persist. Aluminum, titanium, rare earth elements concentrated in landfills and industrial sites. But erosion scatters them. Plate tectonics bury them or drag them into subduction zones. Rivers wash them into the ocean where they disperse. Within a few million years, most concentrated metal deposits would be broken up and spread across such a wide area that they'd be indistinguishable from natural variations. Urban heat island effects would leave no trace. Infrastructure has no chance. Even massive structures like dams erode away quickly. The Hoover Dam, built from concrete and designed to last centuries, would probably be unrecognizable rubble within 10,000 years. After a million years, there'd be nothing left but slightly unusual sediment chemistry, where the concrete leached alkali compounds into the surrounding rock. Fossils of our technology are unlikely. Fossilization is rare. It requires very specific conditions: rapid burial in fine sediment with low oxygen, stable chemistry that allows minerals to replace organic material without destroying structure. The vast majority of organisms that ever lived left no fossils. The fossil record is biased toward organisms with hard parts, shells, bones, teeth, and even then, only a tiny fraction of individuals become fossils. The chances of a smartphone or a car or even a human skeleton fossilizing and surviving intact for millions of years are vanishingly small. What would survive, what Schmidt and Frank keep coming back to, are the chemical signatures, the isotope ratios, the carbon spike. And that's exactly what we see in the PETM. A massive, rapid injection of carbon, 12 enriched carbon into the atmosphere, preserved in sediments as a global chemical anomaly. If you knew nothing about the PETM except the chemical data, and someone told you that signature came from an industrial civilization burning fossil fuels, you couldn't disprove it based on the chemistry alone. The signature fits. The timing fits. The magnitude fits. You'd have to invoke other evidence, paleontological, geological, biological, to argue against it. and that evidence exists. We have fossils from before, during, and after the PETM. We can trace evolutionary lineages through the event. We see the ecological changes, the extinctions, the radiations of new species. None of it looks like there was a technological civilization involved. The fossil record shows natural biological evolution responding to environmental stress, not evidence of agriculture, domestication, construction, or any of the hallmarks we'd associate with civilization. But here's the uncomfortable truth. The fossil record from 56 million years ago is fragmentary. We have fossils, yes, but they're rare. Most species leave no fossils. Most environments don't preserve fossils well. If you tried to reconstruct modern biodiversity based only on what's currently being fossilized, you'd miss most species entirely. You'd have a very incomplete picture of what's alive right now. The same is true for the past. We have snapshots, fragments, hints of what life was like during the PETM. But huge gaps remain. Could a civilization hide in those gaps? Could a species evolve intelligence, build a technological society, and then go extinct, all within a window of time not well represented in the fossil record? It's possible. Unlikely, but possible. That's the point Schmidt and Frank are making. We can't rule it out completely. Not because there's evidence for it, but because the absence of evidence isn't evidence of absence when your detection methods have known limitations. The real question isn't whether there was a civilization during the PETM. The real question is, what caused the PETM, and why can't we explain it definitively? Let's look at the alternatives more carefully. Volcanic eruptions are the most commonly cited natural trigger. The PETM coincides roughly with the North Atlantic igneous province, a period of massive volcanic activity as the Atlantic Ocean was opening up. Lava poured out across what's now Greenland, Iceland, and the sea floor between them. Millions of cubic kilometers of basalt were erupted over a few million years. This kind of volcanism releases enormous amounts of carbon dioxide. When magma rises through the crust, it brings dissolved gases with it. When the pressure drops as the magma reaches the surface, those gases are released. Carbon dioxide is one of the main volcanic gases. Large igneous provinces are known to correlate with climate changes and mass extinctions. The Siberian Traps volcanism is linked to the Permian-Triassic extinction, the worst mass extinction in Earth's history. The Deccan Traps in India are linked to the end Cretaceous extinction alongside the asteroid impact. So, there's precedent for volcanism causing major climate events. But the timing doesn't quite work for the PETM. The North Atlantic volcanism was spread out over millions of years. The PETM carbon spike happened over just a few thousand years. You'd need an incredibly intense pulse of volcanic activity, all concentrated in a very short time window. And the carbon isotope signature from volcanic carbon dioxide doesn't match the PETM signature well. Volcanic CO2 comes from magma, which is derived from Earth's mantle and crust. It has a different isotopic composition than organic carbon. Volcanic carbon is not as depleted in carbon-13 as the carbon released during the PETM. To match the PETM signature, you'd need volcanism that somehow burned through massive coal deposits or ignited organic-rich sediments. This could happen if magma intruded into sedimentary basins rich in coal or oil. The heat from the magma would bake the organic sediments, releasing methane and carbon dioxide with the right isotopic signature. There's some evidence this happened. The North Atlantic volcanism did intrude through sedimentary basins in some areas. But again, the volume of carbon required is enormous. You'd need to bake a truly massive amount of organic sediment to release enough carbon to match the PETM. And you'd need it to happen fast, all within a few thousand years. This is where the conventional explanation starts to feel strained. It's not impossible. Earth's geology can do surprising things, but it requires a very specific sequence of unlikely events, all happening in the right order at the right time. Methane clathrate destabilization, as we discussed earlier, has similar problems. The volume required is huge. The trigger mechanism is unclear. The timing is too sharp. And the isotopic signature doesn't quite match pure methane. Some researchers have proposed a comet impact. A large comet hitting Earth could deliver carbon and trigger climate change. Comets are made partly of organic material, frozen hydrocarbons that formed in the outer solar system. An impact would vaporize this organic material and inject it into the atmosphere. But we have no evidence of an impact at the PETM. No iridium layer, no shocked quartz, no impact crater, no ejector layer. The impact that killed the dinosaurs left unmistakable evidence. The PETM has none of that. So a comet impact seems unlikely. Orbital forcing is another idea. Earth's orbit changes over time due to gravitational interactions with other planets. These orbital cycles, called Milankovitch cycles, affect how much sunlight Earth receives and where that sunlight falls. They drive ice ages and warm periods on timescales of tens of thousands to hundreds of thousands of years. Some researchers have suggested that orbital forcing could have triggered the PETM by warming high latitudes, which destabilized methane in Arctic permafrost or shallow ocean sediments. But again, the magnitude doesn't fit. Orbital forcing causes gradual changes, not sharp spikes. It can shift climate zones, change ice sheet extent, alter monsoon patterns. But it doesn't dump thousands of gigatons of carbon into the atmosphere in a few thousand years. Every conventional explanation has gaps. Every natural mechanism proposed requires special pleading, unlikely coincidences, or conditions that we can't fully verify happened. This doesn't mean the explanations are wrong. It means we don't fully understand what happened during the PETM. There's a missing piece, something we haven't accounted for. And until we find that piece, the question remains open. Let's dig deeper into what the rocks actually tell us. The PETM is identified in geological cores all over the world. Scientists drill deep into ocean sediments, pull up cores that span millions of years of deposition, and analyze them layer by layer. Each layer represents a snapshot in time. The sediments at the bottom are oldest, the ones at the top are youngest. As you move up through the core, you're moving forward through time. And when you reach the layer that corresponds to 56 million years ago, something dramatic happens. The color of the sediment changes. The forum content changes. Forams are microscopic organisms with shells made of calcium carbonate. They live in the ocean, and when they pass on, their shells sink to the bottom and become part of the sediment. Different species live at different depths and temperatures. By identifying which species are present in a sediment layer, you can infer what the ocean temperature and chemistry were like when that sediment was deposited. At the PETM boundary, many deep-sea foram species disappear. They go extinct. Their shells also show signs of dissolution, evidence that the ocean became more acidic. When CO2 dissolves in seawater, it forms carbonic acid, which lowers the pH. At low enough pH, calcium carbonate shells start to dissolve. This is exactly what we see in PETM sediments. The shells are partially dissolved, eroded, weakened. The ocean was eating them away, even as they were being deposited. The carbon isotope ratios in these shells tell the carbon story. Before the PETM, the ratio is stable. Then, right at the boundary, it drops sharply. The negative excursion happens quickly, over just a few centimeters of sediment. In fast-depositing ocean sediments, a centimeter might represent a few decades or centuries. So, the carbon spike happened very fast. Then, the ratio stays low for several meters of sediment, representing tens of thousands of years. Eventually, slowly, it starts to recover. The recovery takes much longer than the onset. The carbon ratio gradually climbs back toward normal over meters and meters of sediment, representing hundreds of thousands of years. This asymmetry tells us something important. Whatever released the carbon, it happened quickly. Whatever removed the carbon, it happened slowly. Natural carbon cycle processes can remove CO2 from the atmosphere, but they take time. Chemical weathering of rocks is the main long-term sink. When CO2 dissolves in rainwater, it forms carbonic acid. This weak acid reacts with rocks, breaking down minerals and releasing ions. These ions wash into the ocean, where organisms use them to build shells. When those organisms pass, their shells sink and get buried in sediments. This process locks carbon away for millions of years. But it's slow. It operates on timescales of hundreds of thousands to millions of years. During the PETM, this weathering process gradually removed the excess CO2 from the atmosphere, but it took 200,000 years to bring things back to normal. 200,000 years of elevated temperatures, acidified oceans, and disrupted ecosystems. Compare this to what we're doing now. We're releasing carbon faster than the PETM. We're overwhelming the natural sinks even more dramatically. The recovery, once we stop emissions, will still take hundreds of thousands of years. We're committing the planet to climate changes that will persist for geological timescales. Even if we stopped all emissions tomorrow, the CO2, already in the atmosphere, will take millennia to be fully removed by natural processes. The warming we've already caused will continue for centuries. Sea level rise will continue for millennia as ice sheets slowly melt and oceans slowly warm. We've set processes in motion that we can't simply stop. The best we can do is limit how much worse it gets. There's another angle worth exploring here. The PETM wasn't the only thermal maximum in Earth's history. It's just the most recent and best studied one. There were earlier thermal events, smaller carbon spikes scattered through the geological record. Some of these are called hyperthermals, brief warming events that share similarities with the PETM but are less extreme. The Eocene epoch, which followed the Paleocene, was generally warmer than today. There were no polar ice caps. Forests grew in Antarctica. Crocodiles lived near the Arctic Circle. Global temperatures were perhaps 10 to 15 degrees Celsius warmer than pre-industrial levels. That's 18 to 27 degrees Fahrenheit warmer. It was a greenhouse world, sustained by higher CO2 levels from volcanic outgassing and other sources. Within this generally warm Eocene, there were several smaller warming spikes. The PETM was just the first and largest. Each of these events shows similar patterns: carbon isotope excursions, temperature spikes, ocean acidification, ecological disruption. The causes are debated for each event. Some might have been triggered by orbital variations. Some might have been volcanic. Some might have involved methane release. But the pattern repeats. Carbon goes up, temperature goes up, bad things happen, then slowly, things recover. It's as if Earth has a tendency toward these events under certain conditions. As if the climate system has instabilities, tipping points where a small trigger can unleash a large response. This is what worries climate scientists about our current situation. We're not just gradually warming the planet. We're potentially triggering tipping points that could lead to much more dramatic changes. The collapse of major ice sheets. The shutdown of ocean circulation patterns like the Atlantic meridional overturning circulation. The release of methane from thawing Arctic permafrost or destabilizing ocean clathrates. The dieback of the Amazon rainforest. Each of these would be a positive feedback, a change that amplifies warming rather than dampening it. And each could happen relatively quickly once triggered. The PETM might have involved exactly these kinds of feedbacks. An initial warming from some trigger, leading to methane release, leading to more warming, leading to more methane release. A runaway process that only stopped when the methane reserves were exhausted or the system shifted to a new stable state. We're playing with the same fire. We're warming the planet into a range where these feedbacks become possible. Arctic permafrost is already thawing, releasing methane and CO2. The Greenland and Antarctic ice sheets are losing mass faster than predicted. The Amazon is experiencing more frequent droughts and fires. Ocean circulation is showing signs of weakening. These aren't hypothetical future risks. They're happening now. And they're happening faster than most models predicted. The PETM tells us that once you start these processes, they're hard to stop. They feed on themselves. They amplify. And they can push the climate into a state very different from what we're adapted to. Let's talk about the species that live through the PETM. What happened to them? How did they respond to such rapid environmental change? The fossil record gives us some answers, though they're incomplete. Marine organisms suffered the most. The deep-sea foram extinctions were severe. Perhaps 35 to 50% of deep-sea foram species went extinct during the PETM. These are organisms that had existed for millions of years, survived other environmental changes, but couldn't cope with the rapid acidification and warming of the deep ocean. Their extinctions created ecological gaps that took hundreds of thousands of years to refill as new species evolved. Shallow water marine life was also affected, though perhaps less severely. Coral reefs, which are sensitive to both temperature and ocean pH, likely suffered. Though the fossil record of Paleocene corals is sparse, so it's hard to say exactly how bad it was. Fish and marine reptiles probably migrated toward the poles seeking cooler water. On land, the changes were dramatic but different. Terrestrial ecosystems didn't collapse in the same way marine ecosystems did. Instead, they reorganized. Species ranges shifted. Animals moved toward the poles or to higher elevations. Plant communities changed composition as temperature and rainfall patterns shifted. Mammals underwent significant changes during the PETM. This is particularly interesting because mammals are our distant ancestors. Understanding how they responded to climate change gives us insight into how evolution works under environmental stress. Before the PETM, mammals were generally small. The largest land mammals were about the size of a large dog. Most were much smaller, rat-sized or rabbit-sized. During the PETM, something called the dwarfing event happened. Many mammal species got smaller. Body size decreased across multiple lineages. Horses, which were already small, became even smaller. Early primates shrank. This dwarfing is documented in the fossil record. You can literally see it in the teeth. As you move up through sediment layers spanning the PETM, the teeth of certain species get progressively smaller. Why did this happen? One theory is that smaller body size is an adaptation to heat stress. Smaller animals have a higher surface area to volume ratio, which helps with heat dissipation. In a rapidly warming world, being smaller might have been advantageous. Another theory is that it's related to nutrition. If plant quality declined due to elevated CO2, having a smaller body requiring less food might have been beneficial. Plants grown under high CO2 often have lower nutritional content. They grow faster but produce less protein and other nutrients. This could have created selection pressure for smaller body size. Whatever the cause, the dwarfing reversed after the PETM ended. As temperatures cooled and CO2 levels dropped, body sizes increased again. Within a few 100,000 years, mammals were back to their pre-PETM sizes or larger. Evolution can respond quickly to environmental changes when the selection pressure is strong enough. But notice, this is evolution we're talking about. Genetic changes across generations. Individuals don't adapt. Populations evolve. And evolution requires time, multiple generations, and sufficient genetic variation. Species that couldn't evolve fast enough went extinct. Species that could evolve or migrate survived. This raises uncomfortable questions about what happens to species today as we warm the planet. Can they evolve fast enough? Can they migrate to suitable habitats? Or will they simply go extinct because the change is too fast? Many species today are already in trouble. Polar bears are losing their sea ice hunting grounds. Coral reefs are bleaching worldwide. Alpine species are running out of mountain to climb as temperatures rise. Rainforest species are losing habitat to droughts and fires. These species are adapted to specific conditions. When those conditions change, they must either adapt, migrate, or perish. Adaptation through evolution takes many generations. Migration requires corridors of suitable habitat, but we've fragmented habitats with roads, cities, and agriculture. Many species have nowhere to go. They're trapped, and the climate is changing faster than they can adapt. The result is the sixth mass extinction currently underway. Species are going extinct at rates perhaps 100 to 1,000 times higher than background extinction rates. We're losing biodiversity at a pace not seen since the asteroid impact 66 million years ago. The PETM caused extinctions, yes, but they were mostly marine invertebrates, organisms with limited mobility and specific environmental requirements. Terrestrial vertebrates mostly survived by migrating or evolving. Today's extinctions are happening across all environments and taxonomic groups. We're losing mammals, birds, amphibians, fish, insects, plants. The causes are multiple: habitat loss, pollution, overexploitation, invasive species, and climate change. But climate change is becoming the dominant threat, and it's accelerating. Here's something most people don't think about. The PETM didn't just affect Earth's surface. It affected the oceans at all depths. Deep ocean temperatures rose by 4 to 5 degrees Celsius, or 7 to 9 degrees Fahrenheit. That might not sound like much, but the deep ocean is normally very cold and very stable. Temperatures in the deep ocean today are around 2 to 4 degrees Celsius, or 35 to 39 degrees Fahrenheit, just above freezing. That cold water is dense, which is why it sinks. The ocean has a layered structure with warm, light water on top and cold, dense water at the bottom. This layering drives ocean circulation. Cold water sinks at the poles, flows along the ocean bottom toward the equator, slowly rises as it warms, and flows back toward the poles at the surface. This circulation, called the thermohaline circulation, distributes heat around the planet. It carries warm water from the tropics toward the poles, moderating climate. It also carries oxygen to the deep ocean, supporting life in the abyss. During the PETM, this circulation probably weakened or changed. Warmer deep water is less dense. It doesn't sink as readily. The circulation slows down. Heat distribution changes. Oxygen delivery to the deep ocean decreases. Parts of the deep ocean may have become anoxic, depleted in oxygen. Anoxic conditions are deadly for most marine life. Only specialized bacteria can survive. The ocean floor becomes a barren wasteland. This is called an oceanic anoxic event, and there's evidence it happened during the PETM in some regions. Black shales, sedimentary rocks, rich in organic carbon, are deposited under anoxic conditions. When there's no oxygen to break down organic matter, it accumulates in the sediment. PETM sediments, in some locations, show increased organic carbon content, suggesting reduced oxygen levels. This creates another positive feedback. Organic-rich sediments can release methane as bacteria break down the organic matter in the absence of oxygen. This methane can bubble up to the surface and enter the atmosphere, adding to the greenhouse warming. So, warming leads to ocean anoxia, which leads to methane release, which leads to more warming. Another runaway feedback. And we're seeing hints of this today. Oxygen levels in the ocean are declining. Deoxygenation is happening in many parts of the world, ocean, partly because warm water holds less dissolved oxygen than cold water, partly because warming is strengthening ocean stratification, reducing the mixing that brings oxygen to deep water. Dead zones are expanding. Regions where oxygen levels are too low to support most marine life. The Gulf of Mexico has a massive dead zone that forms every summer. The Baltic Sea has permanent dead zones. Other ocean regions are experiencing declining oxygen. If this continues, if warming intensifies, we could see more widespread anoxia. Parts of the ocean could become uninhabitable. Fisheries could collapse. Entire marine ecosystems could be lost. The PETM shows us this has happened before, and it can happen again if we push the system hard enough. Now, let's consider another piece of evidence that makes the PETM even stranger: the geographic pattern of warming. Different parts of the planet warmed by different amounts during the PETM. The Arctic and Antarctic warmed the most, perhaps 10 to 15 degrees Celsius or 18 to 27 degrees Fahrenheit. The tropics warmed less, maybe 3 to 5 degrees Celsius or 5 to 9 degrees Fahrenheit. This is called polar amplification. It's a feature of greenhouse warming. When you add CO2 to the atmosphere, the poles warm more than the equator. There are several reasons for this. Ice and snow reflect sunlight, keeping polar regions cool. When warming causes ice to melt, darker land or ocean is exposed. Dark surfaces absorb more sunlight, causing more warming, which melts more ice, and so on. Another feedback loop. Also, the atmosphere at the poles is thinner and drier than at the equator. This makes it more sensitive to greenhouse gas changes. A given increase in CO2 has a bigger temperature effect at high latitudes. The PETM shows exactly this pattern. Maximum warming at the poles, less warming at the equator. It's what you'd expect from CO2-driven greenhouse warming. It's also what we're seeing today. The Arctic is warming about twice as fast as the global average. Arctic sea ice is declining rapidly. Permafrost is thawing. The temperature gradient between the poles and equator is decreasing. This has consequences for weather patterns. The jet stream, the river of fast-moving air that flows around the northern hemisphere, is driven partly by the temperature difference between the Arctic and mid-latitudes. As the Arctic warms and that temperature difference decreases, the jet stream weakens and becomes wavier. This can cause weather patterns to get stuck in place. A heat wave that might normally last a few days can persist for weeks. A storm system that would normally move through can stall and dump unprecedented amounts of rain. This is one reason we're seeing more extreme weather events. The fundamental atmospheric circulation is changing. The same thing probably happened during the PETM. Atmospheric circulation patterns shifted. Rainfall belts moved. Some regions became much wetter, others much drier. The evidence is there in the rocks. Sediment cores from different locations show different patterns of sedimentation during the PETM. Some show increased river flow, depositing more sediment. Others show decreased flow, with periods of drought. Plant fossils show shifts in vegetation types consistent with changing rainfall. The PETM wasn't just about temperature. It was about complete reorganization of Earth's climate system. And that reorganization caused massive disruption to ecosystems that had been stable for millions of years. Species, adapted to specific climate conditions, suddenly found those conditions changing, and they couldn't adapt fast enough. There's an important point to make about scientific uncertainty here. When scientists say they're not sure exactly what caused the PETM, this doesn't mean they don't know anything. It means the available evidence points to multiple possible mechanisms, and it's hard to distinguish between them definitively. This is normal in science. We rarely have perfect certainty about events in the distant past. We build models based on the evidence we have, test those models against new data, and refine them over time. The PETM has been studied intensively for 30 years. Hundreds of papers have been published. Thousands of sediment samples have been analyzed. Multiple hypotheses have been proposed, tested, and refined. We know a lot about what happened during the PETM. We know the timing, the magnitude, the geographical patterns, the ecological consequences. What we don't know is the exact trigger. Was it volcanic? Was it methane? Was it orbital forcing? Was it some combination? Or was it something else entirely, something we haven't thought of yet? This uncertainty doesn't invalidate the science. It shows that science is honest about what it knows and what it doesn't know. And it leaves the door open for new ideas, as long as those ideas are consistent with the evidence. The Silurian hypothesis is one such idea. It's not mainstream. It's not widely accepted. But it's consistent with the evidence in the sense that the chemical signature of the PETM doesn't rule it out. That doesn't make it likely. Just possible. And that possibility is worth taking seriously. Not because ancient civilizations probably existed, but because it teaches us about the limits of our knowledge and the gaps in the geological record. Let's zoom out and think about this from a different angle. What is a civilization, anyway? We tend to think of civilization as cities, writing, agriculture, technology. But at its core, a civilization is just a species that has learned to manipulate its environment on a large scale to suit its needs. Humans started doing this about 10,000 years ago when we developed agriculture. Before that, we lived as hunter-gatherers in small groups, moving with the seasons, following animal migrations, harvesting wild plants. Our impact on the environment was minimal. We were just another species in the ecosystem, one predator among many, taking what we needed but not fundamentally altering the landscape. But agriculture changed everything. It was a revolution, one of the most important transitions in human history. We started clearing forests to plant crops. We diverted rivers to irrigate fields. We domesticated animals and bred them for food, labor, and materials. We built permanent settlements that grew into towns and then cities. We developed trade networks that connected distant regions. We created social hierarchies, governments, religions, art, science. All of this was made possible by agriculture. The ability to produce surplus food allowed some people to specialize in activities other than food production. You could have craftspeople, traders, soldiers, priests, scholars. You could have civilization. And with civilization came increasing environmental impact. Early agricultural societies cleared forests for farmland. They grazed animals that altered vegetation patterns. They built irrigation systems that changed river flows. They mined metals and minerals, leaving scars on the landscape. But for thousands of years, this impact remained relatively local. Agricultural societies affected their immediate surroundings, but the planet as a whole remained largely natural. Then came the Industrial Revolution, and everything changed again. In the late 1700s, we started burning coal on a massive scale to power steam engines. These engines could do work far beyond what human or animal muscle could achieve. They powered factories that produced goods in quantities never before possible. They powered trains and ships that transported those goods across continents and oceans. They transformed how humans lived and worked. Cities grew explosively. In 1800, only about 3% of the global population lived in cities. By 1900, it was 14%. By 2000, it was over 50%. Today, more people live in cities than in rural areas for the first time in human history. And cities require enormous amounts of energy and resources to sustain. Food must be transported from farms, sometimes thousands of miles away. Water must be piped in and waste piped out. Buildings must be heated in winter and cooled in summer. All of this requires energy. And for 200 years, that energy has come primarily from burning fossil fuels. First, coal. Then oil, discovered in Pennsylvania in 1859 and quickly exploited worldwide. Then natural gas, initially a nuisance byproduct of oil drilling, later recognized as a valuable fuel in its own right. These fossil fuels are incredibly energy-dense. A gallon of gasoline contains about 33 kilowatt-hours of energy. That's enough to power an average American home for more than a day. And you can carry it in a small container. This energy density is why fossil fuels became so dominant. Nothing else comes close for portable power. Batteries are improving, but they still can't match the energy density of gasoline or jet fuel. This is why we still use fossil fuels for transportation. Cars, trucks, ships, airplanes, they all run on fossil fuels because the alternatives don't provide enough range or power yet. But burning fossil fuels releases CO2, and CO2 is a greenhouse gas. It traps heat in the atmosphere, warming the planet. This has been known since the late 1800s. Swedish scientist Svante Arrhenius calculated in 1896 that doubling atmospheric CO2 would warm Earth by several degrees Celsius. He was remarkably accurate. His estimates are close to modern calculations. But at the time, this didn't seem like a problem. CO2 levels were only slightly above pre-industrial values. The warming seemed distant and perhaps even beneficial. More warmth might make northern regions more productive for agriculture. Arrhenius actually thought CO2-induced warming would be good overall. He couldn't foresee how rapidly emissions would grow. In the early 1900s, global CO2 emissions were around 1 billion tons per year. By mid-century, they were up to 6 billion tons. By the end of the century, over 23 billion tons. Today, we're at nearly 40 billion tons per year, and accelerating. The curve is exponential. Each decade sees higher emissions than the previous one. China alone now emits more than all developed countries combined in 1950. India's emissions are rising rapidly as its economy grows. Africa's emissions are still low, but will likely increase as the continent develops. Global energy demand is projected to increase by about 50% by 2050. If that demand is met primarily with fossil fuels, emissions will continue rising. And if emissions continue rising, warming will continue accelerating. We're on track for 3 to 4 degrees Celsius of warming by the end of this century. That would put us in the same range as the PETM. We would be recreating Eocene climate conditions. A world with no ice caps, palm trees in the Arctic, sea levels 20 to 30 meters higher than today. That's 65 to 100 feet higher. Every coastal city on Earth would be underwater. Hundreds of millions of people displaced. Entire countries like Bangladesh and the Netherlands largely submerged. Small island nations completely erased from the map. This isn't science fiction. This is basic physics. Ice melts when you warm it. The Greenland ice sheet contains enough ice to raise sea levels by 7 meters, or about 23 feet. The West Antarctic ice sheet contains enough for about 3 meters, or 10 feet. The East Antarctic ice sheet contains enough for about 50 meters, or 160 feet. These ice sheets are already losing mass. Greenland is losing about 280 billion tons of ice per year. Antarctica is losing about 150 billion tons per year. These numbers are accelerating. The rate of ice loss is increasing each decade. At current rates, we'll see 1 to 2 meters, or 3 to 6 feet, of sea level rise by the end of this century. That's enough to cause serious problems for coastal cities. But if warming continues beyond this century, the ice sheets will eventually collapse entirely. It might take centuries or millennia, but it will happen. The physics is clear. Warm air and warm oceans melt ice. Keep warming the planet, and you'll eventually melt all the ice. The PETM had no ice caps. Neither did the Eocene. If we push CO2 levels to Eocene values, we'll create an Eocene climate. And ice caps don't exist in an Eocene climate. This is what scientists mean when they say we're conducting an uncontrolled experiment on our planet. We're changing fundamental parameters of the climate system. We're altering the composition of the atmosphere faster than at any time in geological history, except for major catastrophes like asteroid impacts or massive volcanic eruptions. And we're doing it deliberately, with full knowledge of the consequences. We've known for decades that burning fossil fuels warms the planet. We've known for decades that warming causes ice to melt, sea level to rise, weather patterns to shift, and ecosystems to collapse. We've had countless scientific reports, international agreements, and public warnings. And yet, emissions keep rising. We keep building new coal plants, drilling new oil wells, fracking for more natural gas. We keep flying more, driving more, consuming more. We keep pretending that somehow it will all work out, that technology will save us, that we can continue business as usual without consequences. But the PTM tells us otherwise. The PETM tells us that rapid carbon release has catastrophic consequences. That ecosystems collapse. That species go extinct. That oceans acidify. That climates shift into new states. And that recovery takes hundreds of thousands of years. We're not going to invent our way out of this if we don't also change our behavior. Technology can help. Renewable energy, carbon capture, battery storage, all of these are important. But they're not enough if we keep increasing energy demand. We need to stabilize and then reduce our consumption. We need to transition away from fossil fuels as quickly as possible. And we need to do it now, not in some vague future when it's more convenient or economically optimal. Every year we delay, the problem gets worse. Every ton of CO2 we emit adds to the burden. Every fraction of a degree of warming makes the consequences more severe. Humans started doing this about 10,000 years ago when we developed agriculture. Before that, we lived as hunter-gatherers in small groups, moving with the seasons, following animal migrations, harvesting wild plants. Our impact on the environment was minimal. We were just another species in the ecosystem, one predator among many, taking what we needed but not fundamentally altering the landscape. But agriculture changed everything. It was a revolution, one of the most important transitions in human history. We started clearing forests to plant crops. We diverted rivers to irrigate fields. We domesticated animals and bred them for food, labor, and materials. We built permanent settlements that grew into towns and then cities. We developed trade networks that connected distant regions. We created social hierarchies, governments, religions, art, science. All of this was made possible by agriculture. The ability to produce surplus food allowed some people to specialize in activities other than food production. You could have craftspeople, traders, soldiers, priests, scholars. You could have civilization. And with civilization came increasing environmental impact. Early agricultural societies cleared forests for farmland. They grazed animals that altered vegetation patterns. They built irrigation systems that changed river flows. They mined metals and minerals, leaving scars on the landscape. But for thousands of years, this impact remained relatively local. Agricultural societies affected their immediate surroundings, but the planet as a whole remained largely natural. Vast wildernesses existed where humans had never set foot. The deep oceans remained unexplored. The atmosphere was unaltered. Then came the Industrial Revolution, and everything changed again. In the late 1700s, we started burning coal on a massive scale to power steam engines. These engines could do work far beyond what human or animal muscle could achieve. They powered factories that produced goods in quantities never before possible. They powered trains and ships that transported those goods across continents and oceans. They transformed how humans lived and worked. Cities grew explosively. In 1800, only about 3% of the global population lived in cities. By 1900, it was 14%. By 2000, it was over 50%. Today, more people live in cities than in rural areas for the first time in human history. And cities require enormous amounts of energy and resources to sustain. Food must be transported from farms, sometimes thousands of miles away. Water must be piped in and waste piped out. Buildings must be heated in winter and cooled in summer. All of this requires energy. And for 200 years, that energy has come primarily from burning fossil fuels. First coal, then oil, discovered in Pennsylvania in 1859 and quickly exploited worldwide. Then natural gas, initially a nuisance byproduct of oil drilling, later recognized as a valuable fuel in its own right. These fossil fuels are incredibly energy-dense. A gallon of gasoline contains about 33 kilowatt-hours of energy. That's enough to power an average American home for more than a day. And you can carry it in a small container. This energy density is why fossil fuels became so dominant. Nothing else comes close for portable power. Batteries are improving, but they still can't match the energy density of gasoline or jet fuel. This is why we still use fossil fuels for transportation. Cars, trucks, ships, airplanes, they all run on fossil fuels because the alternatives don't provide enough range or power yet. But burning fossil fuels releases CO2. And CO2 is a greenhouse gas. It traps heat in the atmosphere, warming the planet. This has been known since the late 1800s. Swedish scientist Svante Arrhenius calculated in 1896 that doubling atmospheric CO2 would warm Earth by several degrees Celsius. He was remarkably accurate. His estimates are close to modern calculations. But at the time, this didn't seem like a problem. CO2 levels were only slightly above pre-industrial values. The warming seemed distant and perhaps even beneficial. More warmth might make northern regions more productive for agriculture. Arrhenius actually thought CO2-induced warming would be good overall. He couldn't foresee how rapidly emissions would grow. In the early 1900s, global CO2 emissions were around 1 billion tons per year. By mid-century, they were up to 6 billion tons. By the end of the century, over 23 billion tons. Today, we're at nearly 40 billion tons per year, and accelerating. The curve is exponential. Each decade sees higher emissions than the previous one. China alone now emits more than all developed countries combined in 1950. India's emissions are rising rapidly as its economy grows. Africa's emissions are still low, but will likely increase as the continent develops. Global energy demand is projected to increase by about 50% by 2050. If that demand is met primarily with fossil fuels, emissions will continue rising. And if emissions continue rising, warming will continue accelerating. We're on track for 3 to 4 degrees Celsius of warming by the end of this century. That would put us in the same range as the PETM. We would be recreating Eocene climate conditions. A world with no ice caps, palm trees in the Arctic, sea levels 20 to 30 meters higher than today. That's 65 to 100 feet higher. Every coastal city on Earth would be underwater. New York, London, Tokyo, Shanghai, Mumbai, Miami, New Orleans, all drowned. Hundreds of millions of people displaced. Entire countries like Bangladesh and the Netherlands largely submerged. Small island nations completely erased from the map. This isn't science fiction. This is basic physics. Ice melts when you warm it. The Greenland ice sheet contains enough ice to raise sea levels by 7 meters, or about 23 feet. The West Antarctic ice sheet contains enough for about 3 meters, or 10 feet. The East Antarctic ice sheet contains enough for about 50 meters, or 160 feet. These ice sheets are already losing mass. Greenland is losing about 280 billion tons of ice per year. Antarctica is losing about 150 billion tons per year. These numbers are accelerating. The rate of ice loss is increasing each decade. At current rates, we'll see 1 to 2 meters, or 3 to 6 feet, of sea level rise by the end of this century. That's enough to cause serious problems for coastal cities. But if warming continues beyond this century, the ice sheets will eventually collapse entirely. It might take centuries or millennia, but it will happen. The physics is clear. Warm air and warm oceans melt ice. Keep warming the planet, and you'll eventually melt all the ice. The PETM had no ice caps. Neither did the Eocene. If we push CO2 levels to Eocene values, we'll create an Eocene climate. And ice caps don't exist in an Eocene climate. This is what scientists mean when they say we're conducting an uncontrolled experiment on our planet. We're changing fundamental parameters of the climate system. We're altering the composition of the atmosphere faster than at any time in geological history, except for major catastrophes like asteroid impacts or massive volcanic eruptions. And we're doing it deliberately, with full knowledge of the consequences. We've known for decades that burning fossil fuels warms the planet. We've known for decades that warming causes ice to melt, sea level to rise, weather patterns to shift, and ecosystems to collapse. We've had countless scientific reports, international agreements, and public warnings. And yet, emissions keep rising. We keep building new coal plants, drilling new oil wells, fracking for more natural gas. We keep flying more, driving more, consuming more. We keep pretending that somehow it will all work out, that technology will save us, that we can continue business as usual without consequences. But the PETM tells us otherwise. The PETM tells us that rapid carbon release has catastrophic consequences, that ecosystems collapse, that species go extinct, that oceans acidify, that climates shift into new states, and that recovery takes hundreds of thousands of years. We're not going to invent our way out of this if we don't also change our behavior. Technology can help. Renewable energy, carbon capture, battery storage, all of these are important. But they're not enough if we keep increasing energy demand. We need to stabilize and then reduce our consumption. We need to transition away from fossil fuels as quickly as possible. And we need to do it now, not in some vague future when it's more convenient or economically optimal. Every year we delay, the problem gets worse. Every ton of CO2 we emit adds to the burden. Every fraction of a degree of warming makes the consequences more severe. The window for action is closing. Some climate scientists say we have until 2030 to halve global emissions. If we want to limit warming to 1.5 degrees Celsius or 2.7 degrees Fahrenheit, that's less than a decade away. And emissions are still rising, not falling. We're not even moving in the right direction yet. Some tipping points may already be behind us. The West Antarctic ice sheet might already be committed to collapse. The Amazon rainforest might already be past the point of no return, shifting from a carbon sink to a carbon source. Arctic permafrost thaw might already be releasing enough greenhouse gases to sustain warming, even if we stopped all human emissions. We don't know for certain. These systems are complex and not fully understood, but the risk is real. And the consequences of triggering these tipping points would be catastrophic. Think about what it means to live in this moment. We are the generation that will decide the fate of the planet for the next 100,000 years. What we do in the next few decades will determine what kind of world our children and grandchildren inherit. Will it be a world of climate stability, biodiversity, and opportunity? Or will it be a world of rising seas, mass extinctions, and climate refugees? The choice is ours, not some future generations. Ours, right now. And the clock is ticking. The PETM happened over thousands of years. We're recreating it in centuries. The speed is unprecedented. The consequences will be severe, unless we act, unless we change course, unless we recognize that this is the defining challenge of our time and respond with the urgency it demands. This isn't about saving the planet. Earth will be fine. It's survived 5 major mass extinctions, countless climate swings, asteroid impacts, and volcanic cataclysms. It will survive us too. The question is whether we'll survive ourselves, whether our civilization can endure the changes we're creating, whether we're wise enough to recognize the danger and courageous enough to do what's necessary. The PETM is a test written in rock from 56 million years ago. It shows us what happens when carbon levels spike rapidly. It shows us the consequences of overwhelming the planet's natural carbon sinks. It shows us that recovery is possible but slow, painfully, devastatingly slow. And it asks us a question. Will we learn from this ancient warning? Or will we ignore it and create our own thermal maximum? our own mass extinction? Our own chemical signature in the rocks? The answer depends on what we do next. But agriculture changed everything. We started clearing forests to plant crops. We diverted rivers to irrigate fields. We domesticated animals and bred them for food, labor, and materials. We built permanent settlements that grew into towns and then cities. We developed trade networks that connected distant regions. We created social hierarchies, governments, religions, art, science. And most importantly for this discussion, we started burning things for energy. Wood at first, then coal, then oil and natural gas. Every advance in human civilization has been powered by burning something. We burn carbon-rich materials to release energy. That energy drives everything we do. Industry, transportation, heating, cooking, electricity generation, all of it comes down to combustion. And combustion releases carbon dioxide. For most of human history, this didn't matter. The amount of carbon we released was small enough that natural processes could absorb it without much trouble. Plants grew, absorbed CO2, and locked it away in wood and soil. The oceans dissolved CO2 and buried it in sediments. The carbon cycle stayed roughly balanced. But then we hit the Industrial Revolution. In the late 1700s, we started burning coal on a massive scale. Steam engines powered factories, trains, ships. Cities grew rapidly. Population exploded. Energy consumption skyrocketed. In the 1900s, we added oil and natural gas. We built cars, airplanes, power plants. We spread across every continent. We reshaped entire landscapes to suit our needs. We became a geological force. Our impact on the planet became comparable to natural processes like volcanism and erosion. We are now releasing about 37 billion tons of carbon dioxide per year. That's about 40 gigatons of carbon. And it's accelerating. In just 200 years, we've released enough carbon to measurably change the composition of the atmosphere. CO2 levels have gone from about 280 parts per million before the Industrial Revolution to over 420 parts per million today. That's a 50% increase. The last time CO2 levels were this high was about 3 million years ago during the Pliocene epoch, when global temperatures were 2 to 3 degrees Celsius warmer and sea levels were 49 to 82 feet, or 15 to 25 meters, higher than today. We're pushing the climate toward a state Earth hasn't seen in millions of years. And we're doing it fast. Faster than almost any natural climate change event in geological history. The only comparable event in terms of speed and magnitude is the PETM. That's why the PETM matters so much. It's not just an academic curiosity. It's a case study in what happens when you dump massive amounts of carbon into the atmosphere quickly. And the outcome is not good. The PETM was survivable. Life didn't end. Earth recovered. But it took hundreds of thousands of years, and the recovery wasn't pleasant. Species went extinct. Ecosystems collapsed. The planet was fundamentally altered. If we continue on our current path, we're heading for a similar outcome. We're creating our own PETM. And unlike whatever caused the original PETM, we know exactly what we're doing. We have the data. We understand the mechanisms. We can see the future clearly. And yet, we continue burning fossil fuels at an ever-increasing rate. This is why scientists are terrified. Not because of ancient mysteries or lost civilizations, but because we're watching history repeat itself. We're seeing the same pattern play out that we see in the rocks from 56 million years ago. A rapid carbon spike, warming climate, acidifying oceans, species extinctions. And we know how that story ends. It ends with a planet that's hotter, less stable, less hospitable to complex life. It ends with ecosystems in chaos and species struggling to adapt fast enough to survive. It ends with a geological record that shows a sharp boundary, a moment when everything changed. Future geologists, if they exist, will look back at our time and see exactly what we see when we look at the PETM. A thin layer in the rock, marked by unusual chemistry, elevated carbon isotopes, evidence of rapid environmental change. They'll call it something like the Anthropocene thermal maximum, and they'll wonder what caused it. They'll have theories. Maybe they'll blame volcanic eruptions. Maybe they'll propose some natural mechanism. Or maybe they'll find our plastic, our nuclear isotopes, our cities buried under miles of sediment. And they'll realize that an intelligent species did this to itself. There's another aspect to this that's worth considering. The question of whether civilizations are inevitable or fragile. If intelligence evolves on a planet, does that planet inevitably develop a technological civilization? Or is civilization a rare, unlikely outcome that requires specific conditions? And once a civilization develops, is it stable or does it tend to self-destruct? These questions matter for understanding life in the universe. The Drake equation, formulated by Frank Drake in 1961, tries to estimate how many communicative civilizations exist in our galaxy. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually develops, the fraction where intelligent life evolves, the fraction that develop technology, and the length of time such civilizations remain detectable. That last factor is crucial and completely uncertain. How long does a technological civilization last? Do civilizations last millions of years, spreading across the galaxy and building Dyson spheres and megastructures? Or do they last just a few centuries before destroying themselves through war, environmental collapse, or resource depletion? If civilizations are short-lived, then even if intelligence evolves commonly, the galaxy could be mostly empty because civilizations don't overlap in time. By the time one civilization arises, earlier ones have already disappeared. The PETM offers a troubling data point. If it was natural, it shows that planets can undergo catastrophic climate change even without intelligent interference. Earth's climate is not inherently stable. It can flip into drastically different states relatively quickly. If it was caused by a civilization, it shows that civilizations can alter their planet's climate to the point of self-destruction. Either way, the message is the same. Planets are fragile. Climate stability is not guaranteed. And once you start releasing carbon at industrial scales, the consequences can be severe and long-lasting. This is the Great Filter idea. The Great Filter is a proposed solution to the Fermi paradox. If life is common in the universe, and intelligence is a natural outcome of evolution, then we should see evidence of alien civilizations everywhere. But we don't. The universe appears silent. The Great Filter proposes that something prevents most civilizations from reaching the stage where they're detectable across interstellar distances. Maybe the filter is behind us. Maybe it's incredibly rare for life to start, or for complex cells to evolve, or for intelligence to develop. If so, we're incredibly lucky to exist, and the universe is mostly empty. Or maybe the filter is ahead of us. Maybe civilizations inevitably develop technology that destroys them before they can spread beyond their home planet. Nuclear war, engineered pandemics, runaway climate change, artificial intelligence that doesn't align with human values. There are many ways a civilization could end itself. If the filter is ahead, then we're in grave danger. Every civilization reaches the point we're at now, realizes the danger, and fails to stop it. The PETM could be evidence of this pattern. A species evolves, develops industry, burns through its planet's fossil fuels, triggers runaway climate change, and goes extinct. The planet recovers, eventually. Life goes on. Evolution continues. But that particular civilization is gone forever, leaving only a faint chemical signature in the rock. This is speculation. We have no proof any of this happened. But it's consistent with the data. And it's terrifying because it suggests that what we're doing right now, burning fossil fuels and warming the planet, might be a universal pattern. Every intelligent species might go through this phase, and most of them might not survive it. Let's bring this back to what we actually know. The PETM happened 56 million years ago. It released thousands of gigatons of carbon into the atmosphere over several thousand years. The carbon isotope signature matches organic carbon, consistent with either methane release or combustion of organic material. Global temperatures spiked by 5 to 8 degrees Celsius, or 9 to 14 degrees Fahrenheit. Oceans acidified. Species went extinct. Ecosystems were disrupted for hundreds of thousands of years. Eventually, the climate stabilized and life recovered. All of this is established science. What's not established is exactly what caused it. Conventional explanations involve some combination of volcanic activity, methane release, and possibly organic-rich sediment combustion. These explanations are plausible but incomplete. They require specific conditions and triggering mechanisms that we can't fully verify. The Silurian hypothesis doesn't claim there was a civilization. It claims we couldn't detect one if there was. That our methods for studying deep time have limitations that could hide evidence of industrial activity. This is important methodologically because it tells us something about what we can and can't know from the geological record. It tells us to be humble about our certainty when reconstructing ancient events. And it gives us a framework for thinking about detectability of civilizations elsewhere in the universe. But it doesn't prove anything about the PETM specifically. What it does do is reframe the question. Instead of asking, was there a civilization during the PETM? We should ask, what would we actually see in the geological record if there was? And does the PETM match that prediction? The answer is yes, it does match. The chemical signature fits. The magnitude fits. The timing fits. You can't distinguish the PETM carbon spike from what an industrial civilization would produce based on chemistry alone. You need additional evidence from paleontology, biology, and geology to argue against it. And that evidence exists, but it's fragmentary. We can't rule out a civilization with certainty. We can only say it's unlikely based on what we currently know. This uncertainty should make us uncomfortable. Not because it means there probably was a civilization, but because it means Earth's past is more mysterious than we'd like to admit. We don't have all the answers. We can't explain everything, and some events in Earth's history remain deeply puzzling despite decades of research. The practical implications of all this are what matter most. Whether or not there was a civilization during the PETM, the event itself teaches us about planetary climate dynamics. It shows that Earth's climate can change dramatically and rapidly. It shows that carbon release on the scale of thousands of gigatons has severe, long-lasting consequences. It shows that ocean acidification can drive mass extinction, and it shows that recovery takes hundreds of thousands of years. We are currently on track to release comparable amounts of carbon to the PETM. If we burn all known fossil fuel reserves, we'll release several thousand gigatons of carbon. That's the same order of magnitude as the PETM. The main difference is we're doing it even faster. The PETM released its carbon over 5 to 20,000 years. We're releasing ours over just 200 to 300 years. That's 100 times faster. The climate system can't adapt that quickly. Natural carbon sinks, forests, soils, oceans. They absorb carbon over timescales of decades to centuries. We're overwhelming those sinks. We're releasing carbon faster than the planet can remove it. The result is atmospheric CO2 is accumulating. And as it accumulates, the planet warms. We're already seeing the effects. Global average temperature has increased by about 1.1 degrees Celsius or 2 degrees Fahrenheit since pre-industrial times. Arctic sea ice is declining. Glaciers are retreating. Sea levels are rising. Ocean pH is dropping. Coral reefs are bleaching and dying. Extreme weather events are becoming more frequent and severe. Droughts, floods, heat waves, hurricanes, all of it is intensifying. And this is just from 1 degree of warming. We're on track for 3 to 4 degrees Celsius or 5 to 7 degrees Fahrenheit by the end of this century if we don't change course. At that level of warming, the impacts become catastrophic. Coastal cities flood as sea levels rise. Agricultural systems fail as rainfall patterns shift. Ecosystems collapse as species can't adapt fast enough. Hundreds of millions of people are displaced by climate refugees. Water resources become scarce in many regions. Conflicts over resources increase. This is not speculation. This is what the science predicts based on our understanding of climate physics. And the PETM shows us that these predictions are conservative, if anything. The PETM was worse than our current models suggest our future will be. And the PETM had a natural trigger. We're causing ours deliberately. This is why climate scientists have been sounding the alarm for decades. This is why every major scientific organization in the world agrees that climate change is real, human-caused, and dangerous. This is why we need to transition away from fossil fuels as quickly as possible. Not because of politics or ideology, because the physics and geology are clear. We're running an experiment on our planet that we've already seen the results of. We know how it ends. And it doesn't end well. There's a philosophical dimension to this as well. If we accept that we might not be able to detect ancient civilizations in the geological record, what does that say about our own legacy? What will remain of us in 50 million years? Will future geologists, human or otherwise, be able to tell that we existed? Will they find our plastics, our radioactive isotopes, our chemical fingerprints? Or will we disappear completely, leaving only a thin layer of unusual carbon chemistry? And does it matter? Does it matter? If future beings remember us, does our significance depend on leaving a permanent mark on the planet? Or is our significance in how we live right now, in how we treat each other and the world we inhabit? These aren't scientific questions. They're existential ones. But they're worth asking because they affect how we think about our place in deep time. Humans are unique in our ability to contemplate deep time. We can look back billions of years to the origin of Earth and the universe. We can project forward billions of years to the eventual death of our sun. We can place ourselves in that vast expanse of time and understand how brief our moment is. This perspective should humble us. Everything we care about, every triumph and tragedy in human history, happens in the blink of an eye on geological timescales. We are fleeting. Our cities will crumble. Our monuments will erode. Even our deepest impacts on the planet will fade eventually. 50 million years from now, Earth will look much like it did before we arrived. The forests will have regrown. The climate will have stabilized. New species will have evolved to fill the niches we disrupted. The planet will heal. It always does. The question is whether we'll still be here to see it. Whether humanity survives the next few centuries depends entirely on the choices we make now. Do we continue burning fossil fuels until we trigger a climate catastrophe comparable to the PETM? Or do we transition to sustainable energy sources and stabilize the climate before it's too late? The technology exists. Solar, wind, nuclear, geothermal, battery storage. All of it is technically feasible and economically viable. What's lacking is political will and social coordination. We know what needs to be done. We just haven't done it yet. And the clock is ticking. Let's return to Schmidt and Frank's original question. Could an industrial civilization exist in Earth's geological record and we wouldn't know? The answer, as we've discussed, is yes. After tens of millions of years, very little physical evidence would remain. Chemical signatures would be subtle and easily attributed to natural processes. Only if you knew exactly what to look for and had sophisticated analytical techniques could you detect it. This has profound implications for the search for extraterrestrial intelligence. If we're looking for signs of life on other planets, what should we actually be looking for? Biosignatures, chemical indicators of life, like oxygen or methane in planetary atmospheres. But what about technosignatures? Indicators of technological civilizations. Radio signals are the traditional approach. SETI, the search for extraterrestrial intelligence, has been scanning the skies for decades, looking for artificial radio transmissions. But radio signals require an active, broadcasting civilization. If civilizations are short-lived, we might miss them entirely. Their radio transmissions might come and go in the cosmic blink of an eye while we're not looking. Or they might be beamed in directions we can't detect. Or they might use technologies we haven't thought of. Chemical signatures might be more persistent. If a civilization industrializes, it should leave chemical traces in its planet's atmosphere. Pollutants, industrial byproducts, synthetic molecules that don't occur naturally. We might be able to detect these in the atmospheres of exoplanets using spectroscopy. But we'd need to know what to look for. And we'd need very sensitive instruments. The James Webb Space Telescope and future missions will have this capability. They'll be able to analyze the atmospheres of rocky exoplanets in detail. If there are industrial civilizations out there, we might see their pollution. But here's the catch. If civilizations tend to collapse after industrializing, we might see evidence of dead civilizations. Planets with unusual atmospheric chemistry, signs of past industrial activity, but no active signals, no radio transmissions, no signs of life at all. Ghost worlds. Places where intelligence evolved, built a civilization, altered the planet, and then vanished. This is the dark implication of the Silurian hypothesis. Maybe the universe is full of dead civilizations. Maybe intelligence is common, but long-term survival is rare. Maybe we're surrounded by the ruins of species that couldn't solve the same problems we're facing now. Climate change, resource depletion, social cohesion, existential risk. These might be universal challenges that every civilization faces, and most might fail. We have no way of knowing yet. Our sample size is 1. We know humanity exists. We don't know if we're typical or exceptional. We don't know if our struggles are unique or universal. But the PETM gives us a hint. It shows that planets can undergo rapid, catastrophic changes. It shows that carbon release at industrial scales has severe consequences. And it shows that even if you can't point to a specific cause, the effects are real and measurable. Whether it was natural or artificial, the PETM nearly broke Earth's climate. And we're doing the same thing again right now. Let me be clear about the current scientific consensus. The mainstream scientific view is that the PETM was caused by natural processes. Most geologists believe it was some combination of volcanic activity and methane release. The Silurian hypothesis is considered an interesting thought experiment, not a serious proposal for what actually happened. There is no credible evidence of a civilization during the PETM. No artifacts, no unambiguous technosignatures, nothing that would convince a skeptical scientist. The fossil record shows continuous evolution of life through the PETM without any indication of intelligent interference. All of this is important to state because I don't want to give the impression that there's a scientific debate about ancient civilizations. There isn't. The scientific community overwhelmingly agrees that the PETM was a natural event. What Schmidt and Frank contributed was not evidence of a civilization, but a framework for thinking about detectability. They showed that our ability to detect ancient civilizations is limited by the preservation bias of the geological record. They showed that chemical signatures might be the only persistent trace of industrial activity over millions of years. And they showed that the PETM happens to match what such a signature would look like. This doesn't mean there was a civilization. It means we should be cautious about assuming we definitely know if there was. The absence of evidence is not evidence of absence when your detection methods have known blind spots. This is a methodological point, not a claim about reality. And it's a valid point that has implications for astrobiology and planetary science. But it's being misused by people who want to believe in ancient aliens or lost advanced civilizations. That's not what this is about. This is about understanding the limits of our knowledge and being honest about uncertainty. Science is not about proving things with certainty. It's about building models that fit the available evidence and revising those models as new evidence emerges. The model for the PETM is incomplete. We don't fully understand what triggered it or where all the carbon came from. But that doesn't mean we should invoke extraordinary explanations without extraordinary evidence. The principle of parsimony, often called Occam's razor, says we should prefer the simplest explanation that fits the data. Natural processes are simpler than ancient civilizations. So, until we have compelling evidence for a civilization, we should stick with natural explanations. But we should also acknowledge that our understanding is incomplete and remain open to refining our models as we learn more. That's how science works. The reason this topic resonates with people, the reason it's fascinating and unsettling, is because it touches on deep questions about time, existence, and our place in the universe. We want to believe we're special. We want our civilization to matter, to leave a lasting mark, to be remembered. The idea that we might vanish without a trace, that everything we've built might crumble and be forgotten, is existentially terrifying. But it's also liberating, in a way. If nothing we do will matter in 50 million years, then the pressure is off. We can focus on what matters now, how we treat each other, how we take care of the planet we live on, the lives we touch, the beauty we create, the knowledge we discover and share. None of this will survive deep time, but it doesn't need to. Its value is intrinsic, not dependent on permanence. A sunset is beautiful, even though it fades. A song is meaningful, even though it ends. A life well lived matters, even though it's brief. Our significance doesn't come from leaving scars on the planet that persist for millions of years. It comes from how we live in the present, in the moment we're given. The PETM reminds us of this. Whether it was caused by a civilization or by natural processes, it shows that planets are resilient. Earth survived. Life recovered. Evolution continued. The planet doesn't need us. It was fine before we arrived, and it will be fine after we're gone. But we need the planet. This is the only home we have, and we're part of the web of life that inhabits it. Our fates are tied together. If we damage the planet badly enough, we damage ourselves. If we protect and restore ecosystems, we protect our own future. This isn't about saving the planet. Earth will be fine in the long run. This is about saving ourselves and the millions of other species we share this world with. This is about recognizing that we're not separate from nature. We're part of it. And our actions have consequences that ripple through the entire system. The PETM is a warning from deep time. It shows us what happens when you release too much carbon too fast. The consequences are severe, global, and long-lasting. Recovery is possible, but slow. Hundreds of thousands of years slow. That's not a timescale humans can work with. We can't afford to wait hundreds of thousands of years for the climate to stabilize naturally. We need to act now, within decades, to prevent the worst outcomes. And we can. We have the knowledge. We have the technology. We have the resources. What we need is collective action. Individual efforts matter, but they're not enough. This is a systemic problem that requires systemic solutions. Governments need to set policies that incentivize clean energy and penalize pollution. Corporations need to transition to sustainable practices. Financial systems need to stop funding fossil fuel expansion and start investing in renewables. Educational systems need to teach climate science and systems thinking. Media need to cover climate change accurately and prominently. And individuals need to vote, advocate, and push for change at every level. This is the challenge of our generation. This is the test we're facing. Can we recognize a planetary-scale threat and respond effectively? Can we cooperate across national boundaries to address a common danger? Can we put aside short-term interests for long-term survival? The PETM suggests that this might be a universal challenge. Every civilization that industrializes faces this moment. The moment when their impact on their planet becomes comparable to natural processes. The moment when they have to choose between continuing on their current path or changing course. Some civilizations might pass this test. They might transition to sustainable energy, stabilize their climate, and survive for millions of years. Others might fail. They might continue burning carbon until they trigger runaway climate change and collapse. We don't know which category we'll fall into yet. That depends on what we do in the next few decades. History hasn't been written yet. The future is still undecided. We have agency. We can choose. Tonight, we've explored one of the most intriguing mysteries in geology. The Paleocene-Eocene thermal maximum, an event 56 million years ago that released massive amounts of carbon into the atmosphere, warmed the planet dramatically, acidified the oceans, and drove species extinct. We've looked at the conventional explanations and their shortcomings. We've examined the Silurian hypothesis and what it tells us about the limits of our knowledge. We've considered the terrifying possibility that civilizations might be self-limiting, that intelligence itself might be a great filter. And we've confronted the uncomfortable parallel between the PETM and what we're doing to the planet right now. The truth is, we don't know for certain what caused the PETM. We have plausible natural explanations, but none of them are entirely satisfying. There are gaps in our understanding, pieces that don't quite fit. The Silurian hypothesis doesn't solve this mystery. It adds another layer of uncertainty. It shows that we can't completely rule out the possibility of an ancient civilization based on current evidence. But more importantly, it shows that we're creating exactly the same signature in the rock record right now. Future geologists will look back at our time and see a sharp carbon spike, rapid warming, ocean acidification, mass extinction. They'll see the Anthropocene thermal maximum, and they'll ask the same questions we're asking about the PETM. What caused this? Why did it happen so fast? How did it end? The difference is, they might have a clearer answer. They might find our cities buried under sediment. They might detect our radioactive isotopes. They might identify our plastics and synthetic chemicals. Or they might not. If enough time passes, if the Earth's surface gets recycled thoroughly enough, we might vanish as completely as any hypothetical PETM civilization. All that would remain is the chemistry, the carbon spike, the isotope ratios. The same puzzling signature we see from 56 million years ago. This should humble us. We like to think we're immortal, that our civilization will last forever, that our achievements will echo through the ages. But the geological record tells a different story. It tells us that everything is temporary. Species come and go. Ecosystems rise and fall. Continents drift. Oceans open and close. Mountains erode to nothing. Even the rocks themselves get recycled. Nothing lasts forever. Everything changes. And yet, here we are. Conscious beings who can understand deep time, who can read the history of the planet in layers of rock, who can contemplate our own impermanence and still find meaning in the present moment. That's extraordinary. We're the universe, becoming aware of itself. We're matter organized in such a way that it can ponder its own existence. We're 56 million years removed from the PETM, and we can reconstruct what happened during that event in remarkable detail. We can measure the temperature change, calculate the carbon release, track the ecological consequences. We can use that knowledge to understand our own impact on the planet. We can see the pattern. We can recognize the danger. And we can choose to do something about it. That choice is what matters. Not whether there was a civilization during the PETM. Not whether we'll be remembered in 50 million years. But what we do right now, in this moment, with the knowledge we have. Do we continue on our current path, burning fossil fuels and warming the planet, repeating the pattern from 56 million years ago? Or do we change course, transition to sustainable energy, stabilize the climate, and give ourselves and countless other species a chance at a future? The answer to that question will determine whether we become a success story or a cautionary tale. Whether we're the civilization that recognized the danger and responded effectively, or the civilization that saw the cliff ahead and kept driving anyway. The geological record will preserve our choice. One way or another, we'll leave a mark. The question is, what kind of mark will it be? A brief carbon spike followed by recovery and continued evolution, or something worse? Scientists are terrified, not because they think there was a civilization before us. They're terrified because the PETM shows us exactly what we're walking into. And we're not stopping. We're accelerating. We're running the same experiment Earth ran 56 million years ago. And we already know the results. The planet will survive. It always does. But we might not. And that's what keeps scientists up at night. Not ancient mysteries. Not hypothetical civilizations lost to time. But the very real, very immediate threat we're creating for ourselves. The PTM is a mirror. When we look at it, we see ourselves. We see what happens when you release too much carbon too fast. We see the consequences play out over hundreds of thousands of years. We see the planet transformed. And we have to ask ourselves if that's really the legacy we want to leave. A thin layer of carbon-rich sediment. A spike in the isotope ratios. A mass extinction event. A warming event that took 200,000 years to reverse. That's what we're creating right now. That's the mark we're leaving on the planet. Unless we change course. Unless we choose a different path. The future isn't written yet. We still have time. Not much. Decades, maybe. But enough to make a difference if we act decisively. The PETM happened over thousands of years. We're compressing that into centuries. We can also compress the solution. We can transition to clean energy faster than anyone thought possible. We can protect and restore ecosystems. We can adapt our societies to the changes already underway. We can survive this. We can thrive. But only if we recognize the danger and respond accordingly. The warning is there. Written in rock from 56 million years ago. A message from deep time telling us what happens if we don't listen. The question is, will we heed that warning? Or will we become another mystery for future geologists to puzzle over? Another unexplained carbon spike in the rock record. Another civilization that rose, flourished briefly, and vanished without a trace. That choice is ours to make. Right here, right now. Tonight, we've looked into deep time and seen our own reflections staring back. What we do with that knowledge will determine everything that comes after. The geological record is watching. History is being written. And we're the ones holding the pen,